Okay, sorry for the disturbance, like the projector was not working. So now we can start our lecture. So in our last class, actually, what we did, let me review that logistic regression is different than multiple regressions or the ANOVA or the ANCOVA that we have learned so far. Now what's the difference in the logistic regression? So far we considered that our response variable is continuous. Continuous means it takes values in a certain range. Now we are considering that our response variable is no longer continuous. It's a categorical variable. And we are only considering two categories. So we are saying that logistic regressions, because if the response variable is categorical, then the error term will not follow the normal distribution. So we cannot use the multiple regression or the regression models. So what we have to do, we cannot fit the linear models because they are not now linearly related. So we need to take some transformations to make it linear. And we have seen in chapter 13, I recommend that, okay, there are many situations where if there is some violation of the assumptions here at the end, so here I mentioned that certain types of data have generally accepted transformation will bring them in line with our assumptions. One of the transformation, if the data is count data, we use the square root. If the data is the time, then we use the log. If we have categorical variables with 0 and 1, or we call it the proportion, then we use the logit one. So now we are going to use this transformation. We call it the logist, or we call it the logistic. So here we take the log of odds. So odds, I'll define what is odds, but this is the transformations to make it linear. Yi equal to ln yi over 1 minus yi. Now let's go back to our logistic regression. Now, only difference here is that in simple linear or multiple linear regressions or ANOVA or the ANCOVA, our response variable was always continuous. But now we are considering the response variable that is not continuous. Instead, it is categorical variables with different categories. So we are considering only two categories here. So binary response, we are saying success or failures or yes or no, whatever. And we are considering the quantitative predictors. So quantitative predictors, we know what is quantitative predictors. Now, the goal of our analysis in this chapter is to know whether the levels of the predictor variable can be used to predict a categorical outcomes, whether they fall in this category or the other category. So, as usual, we always try to predict it. So we are going to do the predictions based on our predictor variables. And we would like to predict whether a categorical variable should take success or failures, or whether they fall in this category or that category. So there are many examples that I gave you in the last class. The examples was that, okay, if we would like to know the effect of the age, so age of the patient, let's say if we would like to know whether age of the patient is a useful predictor whether the patient has a coronary heart disease or not. So here you can see our response variable has only two levels, yes or no, present or absent. Or we can say whether a patient is cured after a given time has passed, so whether it is cured or not, based on the dose of a drug. Or we'd like to know the amount of exposure to first-hand smoke, provide information whether they will develop lung cancer or not. So here our response variable is lung cancer or not based on the amount of exposure. Okay. So all these cases you can see we have quantitative predictors, ability, years of education, or age of patients, or amount of smoke. And our response variable is categorical, either right or wrong, or Republican or Democrat, or cute or sick, coronary heart disease or not, cancer or no cancer. So these are our response variable, which is a categorical response variables. Okay. Now we have two categorical outcomes, either yes or no. These responses are binomial, so we are considering only two categories here. If we have multiple categories in our response variable, this is called multinomial logistic regression. But we are considering logistic regression, either it can be simple logistic regression or it can be multiple logistic regression. But multinomial logistic regression means if we have more than two categories in our response variable. So here I said that we are considering either simple or multiple logistic regression. What is simple or multiple logistic regression means our response variable has only two categories. Response has two categories. Now, if our response variable has more than two categories, then we call it the multinomial. So this will be multinomial. Logistic. If response has more than two, three or more. Okay. So in this chapter we are considering basically simple logistic or the multiple logistic regression. That means we are restricting ourselves with the binary outcomes, either success or failures, or yes or no, or whether they have coronary heart disease or not, or whether they have cured or not, like means we have only two categories. But the idea behind this is that if we have more than two categories, this is called the multinomial logistic regression. Now, if we consider only one predictor, this is called simple logistic regression. But if we have more than one predictor, we call it the multiple logistic regression. Any questions about this idea? Now our simple model from before, we know that this is what we always use, the simple model yi equal to beta 0 plus epsilon I. But now we cannot write our model in this form. And we know that our error terms are no longer normally distributed because our response variable is not normal. The response variable is categorical. It's not continuous. So what we can do, we learn how to predict our response variable based on the levels of the different values of the categorical variables. But we'll take some transformation, and the transformation that we are going to use in this chapter, we call it the logistic or the logit transformations. So I am going to use this data set. In the last class I actually used this one, so let me pull up this data here. So in this data I would like to predict whether a person will subscribe to a newspaper or not based on their ages. Okay? So I am considering one predictor variable which is age here, and I would like to predict whether a person will subscribe to a newspaper or not. So look at our response variable here. I am saying whether they will subscribe or not. So it's a two categories. If they subscribe, we call it one If they don't subscribe, we call it 0. So we have 0 and 1. Okay, now I just make it continuous. Okay, the categorical response variables, I just make it continuous to show you that if we just feed a simple linear regression models ideas like this, that okay, fit y by x. Now subscribe is our response variables. Okay, now the age is our factor, that means continuous variables, which is predictor, and we'd like to predict whether a person will subscribe to a newspaper based on their age. And if we fit these models, we get these scatter plots here. So you can see that this is our scatter plot here. What can we see here? We can see all the points are scattered around two levels of the response variable, one at the 0, another one at the 1. And this is what we can see. This is our age, which is our predictor, and subscribe is our response variables. Now the response variable is not continuous. So we can see that we get all the points clustered around the two levels of the response variable. Even though we consider this a continuous, but it's just we can see this one. So based on this, what can we see? And this is the plot you can see here. This I just showed you this one. Now we can see that younger people here tend not to subscribe and older people tend to subscribe. So 1 is they will subscribe to a newspaper, and 0 means they will not subscribe to a newspaper. So the question is that we still have problems to mathematically describe these situations. It would be nice to get something like the form. We cannot write the form in these ways directly because our model is not in this form. Okay, because our response variable is categorical. So we need to do something about this categorical response data. So if we don't have predictor, for example, if we don't have any predictor, so what we are interested in, the response that we not count the success or failures, we'll just say what is the chance or what is the probability of that the person will subscribe to a newspaper. So we'll look at the probability that the person will subscribe to a newspaper. Okay. Could you show again how to make the variable continuous? Yeah, thank you. Okay, let's go back here. So this is what I showed you. So let's say you go to the column info. Okay, now here it was at the beginning, it was like character and the nominal. So these are all in the data set. Now if you want to make it continuous, you just click on these variables here and right click on this and then go to the column info. Now the column info, you can see that data type is character, so you can change it to the numeric, and modeling type is nominal, so you can change it to the continuous. Now click OK, so you can see this becomes a continuous response variables. We are considering this is continuous, but we know that this is a categorical data response. Now we feed the models based on these two. So our response variable is subscribe and our predictor is age. So we drag the predictor into X factor box and then click OK, and then we get this one. Okay, we don't need this one, so maybe we can. Now this is what we can see here. So bivariate fit of subscribe by age. So we can see that younger people don't tend to subscribe, but older people has more chance of subscribing. Now we would like to know what is the chance that the people will subscribe. That means the probability that the person will subscribe to a newspaper. So here the probability that the person will subscribe to a newspaper, that means the y equal to 1. 1 means they will subscribe to a newspaper. 0 means they will not subscribe to a newspaper. Okay. Now how can we find it out? Now we know that this probability that someone subscribe to a newspaper depend on their age. So here we want to know what is about the probability that someone subscribe to a newspaper depending on their age. Now, in this model, we'd like to fit a model that we'd like to know what is the chance that a person will subscribe to a newspaper depending on their age. So that means we'd like to predict whether a person will subscribe to a newspaper based on their age. So we'd like to fit a models like this, and this model is called the logistic regression models, where our response variable is categorical, and we'd like to predict whether, let's say if we consider any examples like this. Okay. So we can say that, okay, we'd like to know whether a person will have, a patient will have a coronary heart disease or not based on the patient age. So here our response variable is categorical with two categories, and it depends on their age. So we'd like to know this. So this is how we can fit the logistic regression. So here we are considering whether a person subscribes to a newspaper based on their age. Now, as we mentioned that this is no longer a linear models. So we cannot fit the linear models here. So if we try to fit a linear models, what happens here? You can see this is the bivariate, if we fit a linear models here, fit the line, and you can see, we know that these values are between 0 to 1. So this is the success or failure. The probability cannot be greater than 1 or less than 0. But when we fit the linear models, we can see that it goes below the zeros here. So that means since our response variable is restricted, that it's a chance of getting the values either 0 and 1. So we cannot go beyond this, so the probability cannot be greater than 1 or less than 0. So when we fit the linear models, we can see that it goes below the 0, and this violates our conditions or our restrictions. So that's why we cannot straightforward fit a linear models and predict the response variable. So what we have to do? So here I said that one way to do that is to just dive in and fit a linear model to this data. The problem is that the lines are unbounded, so they can go on forever in both directions, but the probabilities are bounded above and below by 1 and 0. So linear model won't work in this case. So we need a model that will respect this law. So you can see that here we cannot fit a linear models because these probabilities are bounded by 0 and 1, but if we fit the line, it just violates these conditions. So what we have to do, so we enter the logistic regressions, so we take a linear models and set it equal to the logit. So we just take a transformations. So what is the transformation that we are going to take? So we take a log of the odds. So here ln means the log, and we call it's a logit. Now we define that yi equal to pi I. So what is pi I? Which is the probability of success. So we can say that the probability that a person will subscribe to a newspaper. So in our case, yi equal to 1. So in this case, we are considering yi equal to 1. And we'd like to know what is the chance that the probability that the person will subscribe to a newspaper. Okay. So yi is the probability of success. So yi equal to 1. So this we are calling it pi I. So pi I equal to probability that yi equal to 1. Okay. Now we take the logarithm of the odds. So odds means here we are taking the probability of success divided by 1 minus probability of success. So we are saying that probability of success divided by the probability of failure. So this one, pi is the probability of success, and 1 minus pi is called the probability of failure. So what is the chance that a person will not subscribe to a newspaper? So we take the ratio of these two and we call it, this is called odds. Odds means the chance that the person subscribes to a newspaper divided by the person will not subscribe to a newspaper. And we now take the natural logarithm ln of this. So this is the transformations that we are taking, and this transformation is called the logistic transformations, or we call it the logit. So the logit function is the log odds of success, or we can say just the log odds. So this is the transformation that we take, and we use this transformation to make it linear. So here you can see that logit is linearly related. So logit is equal to beta 0 plus beta 1 xi. So here we have only one predictor, so we are considering beta 0 plus beta 1. Instead of, if you remember, in our usual case we always say yi equal to beta 0 plus beta 1 xi, okay, plus epsilon. But now we cannot fit these models. This is the linear models case. But now we cannot fit this model. So what we use, instead of fitting the model in this way, linear models, so we take a transformation of this y. So, and then we make it linear. So we say that logit of this pi I, that means this is pi divided by 1 minus pi, and then we say that is equal to beta 0 plus beta 1 xi. So this is the whole idea behind this. Any questions what I said so far? Okay, now so by default, JAMP consider the lower one as the reference categories, but we can change it by Bell ordering. So how we can change it? So if you go here and click on the what is called the columns and column properties and the Bell orders here, and then you can change it. Okay, so if you reverse this one, so it will be considered the 0 as our, now they consider the 0 as our reference category and 1 is the probability of success. But if you want to change it, you can just do the reverse ordering. So reverse ordering, they will consider 1 as the reference category and 0 is the probability of failure. But we would like to know the probability of success, so we just keep like this. So this is how you can sort the order. Okay. This is the custom order. They always put the lower one as the reference category, higher one as the one that we'd like to use. But if you want to change this one, you can change it. Let me show you one more time. If you go to the and select the columns and right click on it, and then you go to the column properties and then Bell orders. Okay. But we are not doing because we would like to predict like this. This is what I said that. So while we and most humans consider one to be a success, so JAMP, other software, they just model the lowest value by default. So the lowest value means the here the reference category. So in JAMP, if you want to model the probability of success, you must choose Bell ordering, and in the column properties of and tell it the reverse the data order that I just told you. And even the JAMP example page has a strong. Okay. Now, if you want to understand the probabilities more directly, we use the inverse logit on both sides, and we are back in the real data. Okay, now I showed you in the last class how we can get this part from this one. You can see that this is what actually we have y ln pi divided by 1 minus pi is equal to beta 0 plus beta 1 x. Okay, xi. Now if you take, like, if you just take the inverse of this logit, or we can take just that, okay, pi 1 minus pi will be e to the power of this. Now if you just manipulate this one, we get pi I equal to this. And this is what we get it here. Very simple, I showed you in the last class. And you have seen how we can do this one. Okay, now we get this on pi I equal to this. Now, if pi I equal to this, then we can get this on. Simply just we divide this on by here, and we can get this on. Okay, so this result in a curved model and feed our data directly. So what is this on? Pi I is the probability of success. So we can say the probability that y equal to 1, condition that we know that it depends on the variable x. What is x here? The age. So here we are considering the probability, okay, our response probabilities that we depend on x. So we need a model that is look like this. So we'd like to know or want to fit the model, the probability that someone subscribed to a newspaper, and then that depends on the age. So here, someone subscribed or does not subscribe to a newspaper depending on the age. So depending on the age here you can see, so probability that someone subscribed to a newspaper which is y equal to 1 depending on their age, which is x. And this is what we call it the pi I. And this pi I just showed you how to get this one in this form. And this is what we are looking for. Okay, we'd like to know what is the chance that someone will subscribe to a newspaper. Now, if you fit the logistic regression models, and you can see that younger ages have lower probabilities of subscribing and older ages are associated with higher probability of subscribing. So here you can see younger age, when the person is younger, is a lower chance that they will subscribe to a newspaper. But when the person is getting older, you can see that the probability is getting higher and higher. So how we can fit this on? The logistic regression model I will show you in JAM. But from this we can see this looks like an S shape. So this is an S shape. So what this tells us, it tells us that, okay, what is the chance that someone will subscribe to a newspaper depending on their age? So we can see that if the person's age is lower, the chance of subscribing to a newspaper is lower. If the person's age is getting older, you can see it's getting higher and higher and higher. That means the chance that they will subscribe to a newspaper is higher. Now another thing that you can notice now, that now when you fit the logistic regression, now it's bounded by 0 and 1. But when you fit the linear models, you have seen that it was going below the 0. And that's why we use the logistic one. So you have seen that linear model is goes below this. Okay. Now, let's go back and fit this logistic regression one. Okay. Analyze, fit models. Okay. Now we'd like to predict the subscribe based on age. Now, you can change here from the standard least square here. Everyone can follow me. So here you can see what I am doing. Standard least square, you need to change it to the generalized linear models. Okay. Now when you change to the generalized linear model, they're going to ask you what is your distribution. So this is the binomial. So we are only considering two levels. And the link function, when you choose the binomial, it gives you the link function is logit. And we are using the logit one. Is that clear how I did it? Can you follow me with the jump? Okay. So let me go over one more time. Analyze, fit model. Subscribe is our response variables. Age is our predictors. Then you change this personality, go to this part here. And change it to the generalized linear models. Select the distribution as the binomials. When you select the binomials, the link function will automatically be logit. And then you can see this graph that I just showed you in my lecture notes. So now you can see that when the person or the chance that the person will subscribe to a newspaper depends on the value of the age. When they are younger age, the chance is very low. You can see it's very low, far from the 1. when they are getting older and older, it's getting higher chance of subscribing to a newspaper. Now, let's go back. Now, if we look at the estimated parameter models here, so this is the estimated parameter model. I'll come back to the whole model test later on. But if you look at the estimated parameter models here, you can see this is no longer the t-test, now they are doing the chi-square test. So we always look at the predictor here. We can see our intercept is negative and the slope is positive. Now, one thing you can notice here, we can see that intercept here is positive. By why it's showing that this is negative? I'll explain this one. But you can see that the most important part we look at age. So we can see age is a useful predictor to predict whether a person will subscribe to a newspaper. Because you can see age, the p-value is lower. Now, how can we interpret these two values? This is not in our simple linear regression case that where we can say for every 1 unit increase in age, the predicted value of y will increase by 0.131. No, because now we are not fitting a linear regression model. Rather, we are fitting a logistic regression model. So, what will be our compact model and what will be our augmented model? So here, this one is this hypothesis test. That means we are saying that beta 1 equal to 0, beta 1 is not equal to 0. So if beta 1 equal to 0, you can see what happens to this one. This is our model now. If beta 1 equal to 0, that means this part will be 0, so it will be just e to the power beta 0. So divided by 1 plus e to the power beta 0. This is our simple regression models here. I mean the compact model, not the simple linear. So this is a compact model. Now augmented model, that means we are using the A, so we can say that augmented model is pi I equal to e to the power beta 0 plus beta 1 xi divided by 1 plus e to the power beta 0 plus beta 1 xi. So you can see that our compact and the augmented model in the logistic regression is totally different from what we have seen in the simple linear regression models, because we are using these transformations. Now we see that there is a positive estimate for age, for x value, and the negative estimate for the intercept. But we know that the probabilities cannot be less than 0. But why we can see, and from the above plot also we can see that is not, intercept is not 0. But the question is that why you can see this is negative. So we see that the intercept is positive from the plot. These estimates, the reason is that these estimates from the logistic regression cannot be interpreted the same way that we can interpret the linear regression model, that means simple linear or the multiple regression. The intercept is not intercept for the linear models. So this is the value of B0 in the estimated logistic regression equation. Okay, so this B0 is the estimated logistic regression. Okay, so what is the value of B0 here? We are saying that when x is 0, what is the chance that they will subscribe to it? So this will be just e to the power beta 0 plus 1 plus e to the power beta 0. Now, so similarly, the estimate of beta 1 is not the slope in a linear sense. This is the estimate of B1 in the logistic regression equation. Now, that's why we can see that this is negative and this is positive here. But this is the value of where beta 1 is 0. That's fine. So this is this one. What is the chance that someone will subscribe to a newspaper when there is no age? So e to the power beta 0 plus 1 plus e to the power beta 0. This is the value of this one. Now the general relationship between the beta 1 and our response is said. So if beta 1 is positive, we say that the response tends to increase as the predictor increases. If beta 1 is negative, we can say the response or the probability that it will decrease. If the predictor increases, beta 1 is 0, that means there is no relationship between the response and the predictors. But when we say about this one, it is not the intercept in the linear model, it is not the slope in the case of the linear models. It is rather like these situations. So however, we can see that we are no longer talking about linear association. If we look at the plot again, you can see that the rate at which this probability increases or decreases will change depending on the value of the predictor. So this probability, here now we are considering the probability. So this will increase or decrease depends on the value of what is called the predictor, in our case X. So what is the chance that the person will subscribe to a newspaper? It depends on the value of age. So now we are not saying that every 1 unit increase in age. Now instead of saying like this, we are saying that what is the chance a person will subscribe to a newspaper based on their age value. So if we say that there is no age, so this value will be e to the power beta 0 plus 1 divided by 1 plus e to the power beta 0. If we have age, then this value will be like this. So we plug in the value of age and it depends on this. So this is the one that we are describing, and this value will come from these two situations. Now the logistic regression parameter actually tells us the log odds. Okay, so we will discuss this one in the next class, more details. Unfortunately today we couldn't finish everything. Hopefully in the next class I will discuss all these details, but I already did the data analysis, but I will discuss about the results and how to find the models, and you can see how to get the predicted values and everything, and how to interpret this one. So this will be in our homework. There is one question like this. Any questions from you so far? So today basically we did the review from the last class. We didn't do the new things. Okay, so if you don't have any questions, then I can end the meeting and hope to see you in the next class, okay?